Let's take a look at the last part of the related rates problem dealing with the ladder sliding away from the wall. So this is at the bottom of page 299. So we've got the ladder sliding down the wall. It's 25 feet long, and the base of the ladder is being pulled away from the wall at 2 feet per second. So we want to find the rate at which the angle formed by the ladder and the wall of the house is changing when the base of the ladder is 9 feet from the wall. So we're going to need a different diagram this time. I mean, it's going to be the same basic picture because we've got the same basic dynamic between the ladder and the side of the house and the ground. But this time, the things that are changing is that this is x of t, and we're not really concerned about the distance from the top of the ladder to the ground, but we are interested in that angle there between the wall and the ladder. All right, and once again, we've got that this side is always equal to 25. So given that, what is the relationship between theta and x that we can come up with? Once again, this is a right triangle. So what we're going to do is we're going to use some trig. So what is the trig function that relates the opposite side of a triangle with the hypotenuse? Well, let me think for a minute. We've got some old horse caught another horse taking oats away. So we've got the opposite and the hypotenuse. So the function we want is sine. And so the equation that relates theta and x is that sine of theta is equal to opposite over hypotenuse. So sine of theta is equal to x over 25. And so now that we've got that, we're going to differentiate both sides of the equation with respect to time. And what's the derivative of sine theta with respect to time? Well, the derivative of sine is cosine, so that would become cosine of theta. And then we're going to add that factor of d theta dt. And what's the derivative of x over 25 with respect to time? Well, that's just a linear function. So that's going to be 1 over 25 times dx dt. Okay, and we know that dx dt is equal to 2. That's the fact that we've been carrying on this whole problem. Dx dt is equal to 2 because the base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So we've got, just kind of rearranging things, d theta dt is equal to, turning that into 2, it's 2 over 25 times cosine of theta. All right, and so what we need to do is we need to find out what theta is at this specific instant. All right, so I like drawing a separate diagram here just to make it clear that we're talking about a specific instance in time and not just the relation between theta and x that's true at all times. So at the specific moment in time, that's 9 and that's 25. And so what we've got here off to the side, I'm going to say that the specific value of theta, sine theta, is equal to 9 over 25. But I don't want to know sine theta. I want to know cosine of theta. So I'm going to solve for theta. So theta is equal to the inverse sine of 9 over 25. And so cosine of theta is equal to the cosine of the inverse sine of 9 over 25. And now that I've got all that, I'm just going to shove it into my calculator. So I've got my calculator. I've got to make sure I'm not in degree mode. I've got to shift over to radians mode because all of calculus is in radians. Radian measure is the only one where the derivative of sine theta is equal to cosine theta. And there isn't some extra factor that we need to work out. So radians is important. All right, so 9 divided by 25 is equal to 0.36. And I want to calculate the inverse sine. And then I want the cosine of that. So this is the angle, theta in radians, and the cosine of that is equal to 0 0.933. All right, and now I'm going to substitute that into here. That's equal to 2 over 25 times 0.933. 2 divided by 25 times 0.933 is equal to this. All right, so d theta dt, the rate of change of the angle, is 0.0857. And what's my units? I'm talking about the change in an angle over time. All right, so we've got to ask ourselves, what do we measure angles in and what do we measure time in for this problem? So angles in calculus, we always measure that in radians. And time, we've been measuring in seconds for this problem, for this whole problem. All right, so this is talking about the change in angle. Let's double check. Does it make sense that this is positive? Give this a little bit of thought. Well, here's my ladder, and it gets pulled away from the wall. So as x is increasing, that angle should be increasing. So a positive measure of radians does make sense for this problem. Okay, so this has really been a nice set of 3 problems to do. So we're seeing about problems where we're relating multiple variables. We're talking about problems where we're adding in extra functions. We're thinking about the relation between x and y, and then we needed to throw in area. And we also saw a problem where we needed to deal with some trig definitions instead of just using, formula for area or volume or the Pythagorean theorem. So lots of good examples in this problem. I approve.